Hi everybody, the purpose of this video is to go over section 3 of chapter 9, and here we are going to talk about determinants and how they can be used in solutions of linear systems. So we are going to talk about determinants. We are going to also describe this magical thing called a cofactor and how a cofactor or the collection of cofactors can be used for determining the determinant of a matrix of arbitrary size. And then we will discuss a few determinant theorems which will hopefully make your life easier. Then we will conclude with Cramer's rule, which is how we can use a determinant or a collection of determinants to solve linear systems. Okay. This right here is a 2 by 2 matrix. As you can see, a matrix is nothing more than a collection or an array of numbers. This right here, denoted by the vertical lines, is the determinant of this particular matrix. Notice that the determinant is a number, and the value of the determinant is the product of these two numbers divided by minus the product of these two numbers for the case of a 2 by 2, which of course gives us this particular formula. And that brings us to this example. Let's find the determinant of this particular matrix. Well, once again, the determinant of A, which symbolically would be essentially just the matrix between two vertical lines. That is going to be the product of 5 and negative 4 minus the product of 2 and negative 8. That will be 20, negative 20, minus negative 16, which will be 20, negative 20, I keep on forgetting that negative sign, plus 16, which will be negative 4. So the determinant of the matrix A is negative 4. That's all there is to it. What about the determinant of a 3 by 3 matrix? Well, here is our 3 by 3 matrix in general form. Now keep in mind that when I say it's a 3 by 3 matrix, the first column tells you the number of rows, and the second column tells you the number of columns. Furthermore, in this general notation, the subscripts, the first subscript tells you which row the element belongs to, and then this second subscript tells you which column the element belongs to. So this is in the third row, first column, third row, second column, and so forth. Nonetheless, the determinant for this is governed by this particular equation, which is what the heck is going on here? Well, nonetheless, this is how you compute. This is how you can determine the determinant for a 3 by 3 matrix. Having said that, there is a more systematic way of showing this, and that is like this. The determinant of A is going to be equal to A11 times the determinant formed right here. Okay, so minus A21, this number, times the determinant formed by this matrix, or more importantly, the matrix that results when you exclude the row and column that includes A21, and then finally, and then plus A31 times the matrix that results when you exclude this row and this column, and that gives us this particular form, which is more systematic. Now notice that this right here is the element, and then this right is a particular element, and this right here is a cofactor of the element. Similarly, A21 is an element, and then minus this quantity is what we call a cofactor, and of course the same thing here, this is called a cofactor. So this is what we have. The determinant of each 2 by 2 matrix is called the minor of the associated element in A. The symbol Mij is the minor that results when row A and column J are eliminated. So what does that mean? Well, if your element is A11, then this is your minor. If your element is A21, then this is your minor, and you can see that by removing the row and the column that you have. And what do you have left? You have A12, A13, A32, A33, and that is your minor. And we can use that approach to find the minor for any other element in the matrix. Okay, so if that's the minor, what is the cofactor? Well, then the cofactor is going to be -1 times the ith plus jth column of the particular element times its minor. So the cofactor of Aij is -1 raised to the I plus jth power times Mij, or similarly, the cofactor of A32 is going to be equal to -1 times the 3 plus 2 power, or the 5 power, times M32, whatever that is, which is just going to be -M32. So how do we find cofactors? Well, here we are. Here we have the, well, you want to find the cofactor of 5, 0, and 4. Basically, these values right here. Well, notice that 5 is in column 1 and row 1, so this is A11. Okay, so the cofactor of 5 is going to be -1 times 1 plus 1 times the minor for that the minor for the position for element 1, 1, which is going to be, well, -1 squared is just simply 1, and this is going to be the determinant of the matrix when this row and this row are removed, which is going to be the determinant of 2, -9, 1, and 3, and that is going to give us 2 times 3 is 6, minus 1 times -9 is -9, and that will give us positive 15. So the cofactor of 5, and we will call that A11, is equal to 15. Okay, well, what about 0? That's at location A21. So this is going to be equal to -1 raised to the 2 plus 1 power times the minor associated with the element at location 21. Okay, well, you can find the minor by defining the determinant of this particular matrix. And of course, also, -1 raised to the 3rd power is going to be -1, so we're going to have minus the determinant of -1, 6, 1, and 3. And that's going to be minus, okay, -1 times 3 is -3, minus 1 times 6. Well, actually, I got ahead of myself. 1 times 6 is -3 minus 6 will be -9, but we're not quite there yet. This is going to be equal to this is going to be 6. That is going to be -9 or 9. So this is equal to 9. And then finally, for this one, well, this is that location A31. Okay, so that is going to be equal to -1 raised to the 3 plus 1 power times the minor associated with position 3, 1. That is going to be, well, this is going to be -1 to the 4th power, or 1. And then the determinant is going to be, the minor is going to be the determinant of these 4 elements here. So we're going to have +1, the determinant of -1, 6, 2, -9. Okay? -1 times -9 is 9, minus 2 times 6, which is 12, and that is going to give us -3. So here, A31 is equal to -3. Well, that is simply great. What are these cofactors and minors have to do with us and determinants? Well, it provides for us an algorithm which will allow us to define the determinant of any square matrix of arbitrary size. And essentially what we need to do is multiply each element or row in any particular column by its cofactor. Okay, and that's going to give you, and that will give you a product. You sum all those products up, you have the determinant. And you're going to have to do this by hand for a 3 by 3 matrix. A matrix of that's a matrix that's any larger, it gets a lot more complicated because you are finding you will be using your cofactors, and if it's a 4 by 4 matrix, you will break it down to 4 determinants of a 3 by 3 matrix, which will then have to be broken down to 3 determinants for a 2 by 2 matrix for each of the 3 by 3 matrices. So as you can see, it gets more and more complicated. In this example, we want to find the determinant of the exact same matrix that we used to determine what the cofactors were, which is kind of cool. We already know what the cofactors are. We know that, well, before we do that, let's just come back to how we compute the determinant. The determinant, and again, remember what we're going to do is we are going to multiply each element in any row or column of the matrix by its cofactor. So the first thing that we want to do is we want to choose which row or column we might want to use. And I'm thinking we should probably use this one. Why? Well, because there's a 0 there, which makes one of the operations trivial. And the second reason is because, well, we already computed the cofactors for them, so this should be pretty straightforward. So this is going to be equal to 5 times the cofactor at that location, which is A11, plus 0 times the cofactor at that location, and we don't really care what it is, because whatever it is times 0, it's going to be 0, plus 4 times the cofactor for that location, that's going to be A31. Now, this would also be equal to negative, 4 times the cofactor associated with A31 plus 1 times the cofactor associated with A32 plus 3 times the cofactor associated with A33. They will give you the exact same value. So you always want to use the one that's easier to produce, which in this case will be this right here, since 1, we have a 0 that we can deal with, and 2, we have we already computed the cofactors. So what do we have for A11? For A11, we had that A11 was equal to 15. We had that A1 and that A21 was equal to 9, not that it matters. And then we had that A31 was equal to negative 3. So in this particular case, our determinant is going to be equal to 5 times 15 plus 0 times 9 plus 4 times negative 3. That will give us 75 minus 12, which will be equal to 63. Now, and once again, if we use this approach, we would get the exact same result. Yeah, what the hell. So that would be 4 times the cofactor associated with A31. That is going to be 9 minus 12. Oh, so that's kind of convenient. It's negative 3. Well, of course, because it's the exact same one that we did before. All right. Plus 1 times the cofactor associated with that particular matrix, which is going to be 5 times negative 9, which is minus 45. Minus 0. and that's going to also be times -1, since that's going to sum to that, since we have I to the 2 plus 3 power, which is going to give us negative, and then plus 3 times 5 times 5 times 2, which is 10, minus 0 times -1, which is 0, and that's going to give us -12 plus 45 minus 30, and that will give us, well, 45 minus 12 is 33. Actually, that should be plus 30. 33 plus 30 is equal to 63. So once again, you get the exact same result no matter which row you choose. So you actually want to use the row that makes the math easiest for you. All right, what else do we have? Okay, well, it turns out that what you've noticed that the sign array for your cofactors is going to follow this, and this is a direct consequence that the sign is determined by -1 to the I plus j power. And here I plus j is even, so we have positive value, odd, even, odd, and so forth. So that's how this basically shows you the matrix, or the values, or the signs associated with each of the cofactors. And this brings us to determinant theorems. Okay, and we have a total of 7, and these could be pretty useful depending upon what it is we need to do. This one right here is very useful. If you have if every element in a row or a column of a particular matrix is 0, then its determinant is 0. If the rows of matrix A are actually the columns in matrix B, and that's also kind of like saying that if A is equal to what we call the transpose of B, then they have the exact same determinant. If any two rows of a matrix are interchanged to form another matrix, or if any two columns are interchanged, then it turns out that the determinant of matrix B is going to be the negative of the determinant of matrix A. Did not see that one coming. Okay, and then suppose that matrix B is formed by multiplying every element of a single row or a single column by some real number k, by some scalar k, then it turns out that the determinant of B is going to be equal to k times the determinant of A. All right, if any two rows or columns of a matrix are identical, then its determinant is equal to 0. And changing the row or a column of a matrix by adding to it a constant times, there should be an S there, another row or column does not change the determinant of that matrix. And then finally, if the determinant is in triangular form, having either zeros above or below the main diagonal, then its determinant is nothing more than the product of the elements on the main diagonal. And we're going to use them in a couple of examples. So here, we want to use the determinant theorems to evaluate this particular determinant. Okay, well, one of the things that we can do is use Theorem 6. Well, how is Theorem 6 going to work for us? And what the heck is Theorem 6 again? Well, this is Theorem 6. We want to change a row or a column of a matrix by adding to it a constant times some other row or column, because that will not change the determinant of a matrix. So chances are, if we actually maybe changed one of these rows, things might be a little easier for us. So what we could do is use Theorem 6, and we could add or subtract 5 times row 1 here. If we did, we're going to have a new determinant. It's going to be equal to 2, 1, 7, -4, 0, 8. And then here we are going to have 6 minus 5 times 2, which is 10. That will be -4. Then we will have 5 minus 5, which is 0. We will have, there should be a 2 here. We will have 21 minus 5 times 7, which is 21 minus 35, or -14. and then we want to compute the determinant of this by actually picking the row and then adding the product of the element, or picking a row or column, and then by adding the product of the elements to that particular row or column. And chances are, and as I think you guys can probably see, we probably want to use this row right here, okay? Because then that's going to be, the determinant is going to be equal to A12 times its cofactor plus A22 times its cofactor plus A32 times its cofactor. Well, A22 and A32 are equal to 0, so this reduces to A12, which is 1, times its cofactor, which is going to be equal to -1 to the 1 plus 2 power times, okay, well, we'll remove those. It's going to be -4 times -14 minus -4 times 8 okay, well, we have a lot here. 1, this is -1. 1 times -1, that's just minus. -4 times 14 is 56. Minus -4 times 8 is -32. Okay, 56 minus -32, that's 56 plus 32. All this becomes equal to -88. Okay, so basically what do we do here? We use theorem 6 to make the computation of the determinant just a little bit easier. Okay, what about this one? Well, this one has theorem 7 all written all over it. So here we want to use theorem 7. It is of upper triangular form. And what is the determinant here going to be? Well, it's going to be equal to the product of the diagonals. 1 times 4 times -2 times 9. That is going to be equal to -8 times 9, which of course is -72. So with an upper triangular form or a lower triangular form, it's a piece of cake. And this brings us to the very last thing that I want to talk about in this particular video, and that is Cramer's rule. This is what Cramer's rule says. Given any system of equations, this is for two equations, then if D is not equal to 0, then this system will have unique solutions, and those solutions is going to be equal to dx, which is a determinant, divided by d for x, and then y is going to be equal to dy divided by d. So what is d? Well, d is nothing more than the determinant formed by the coefficients. dx is formed by replacing the coefficients in the first column with the constant values in the first column, or the constant values, and finding the determinant. dy is found by replacing the coefficients in the second column by the constant value and then finding the determinant. That's all there is to it. What about three equations? Well, here you go. Here are our three equations, and if D is non-zero, then there is a unique solution, and the solution is going to be described like this. Basically the same format. Of course, now the D is a 3 by 3 determinant, and of course first, and once again, D is nothing more than the determinant with the coefficients. dx is the determinant where the first column is replaced with where the first column is replaced with the constant values. dy is the determinant where the second column is replaced with the constant values, and yes, for dc the third column is replaced with the constant values. So once again, same type of ratio, but now we have a 3 by 3, and you guessed it, if we actually had 4 or more, well, then we would have bigger determinants and more determinants to compute. For our second to last example, we want to use Cramer's rule to solve this system of linear equations. And I don't think I'm going to have enough room to do this here, so I'm going to try to do this in OneNote. Okay, so here we are in OneNote, and the first thing we're going to need to do is write these in the standard form. Specifically, you want to write these as with the constants on the other side of the equality, and that will give us 2x minus 4y plus z is equal to 19. 4x plus 6y minus z is equal to negative 15. And then finally x plus y plus 2z is equal to 11. Okay, so once again, x is going to be equal to dx divided by d. Y is going to be equal to dy divided by d. And then z is going to be equal to dz divided by d. What is d? Well, d is going to be the determinant 2, negative 4, 1, 4, 6, negative 1, 1, 1, 2. And we can compute this, and we're going to compute this using the third row. Okay, and what's that going to look like? Well, that is going to look like, well, 1 times the cofactor associated with 3, 1, plus 1 times A3, 2, plus 2 times A3, 3. And then A3, 1 is going to be negative 1 to the 4th power times the determinant negative 4, 1, 6, negative 1. Okay, A3, 2, that is going to be equal to negative 1 raised to the 5th power times the determinant 2, 1, 4, negative 1. And then we're going to have plus 2 times A3, 3, which is going to be negative 1 to the 6th power. And the associated determinant is going to be 2, negative 4, 4, and 6. Computing all that, we are going to have, well, that's just going to be 1. And we're going to have 4 minus negative 6. 4 minus 6. I just misspoke there. Plus negative 1 times negative 2 minus 4. Negative 2 minus 4. Plus 2 times 1, or just simply 2. I forgot the vertical line there as well. Times 12 minus negative 16. Or 12 plus 16. Okay, so that is going to give us negative 2. Oh, I forgot the negative 1 there. It's supposed to be negative 1. Negative 1 times negative 2 minus 4. So negative 2 plus 6, and then plus 28 times 2, or 56, and that will be equal to 60. Okay, so that is d, and is non-zero. Okay, now dx is going to be equal to 19 -4, 1, -15, 6, -1, 11, 1, and 2. And that will be equal to 90. dy is going to be equal to 2, 4, 1, 19 minus 15, 11, 1 minus 1, 2, and that will be equal to -150. And then finally dz, that determinant is going to have the form 241, -4, 6, 1, -4, 6, 1, 19, -15, and 11. So there are where the constant terms are. And that will be equal to 360. And with that, we can figure out what x, y, and z are. X is going to be equal to dx over d. That is going to be 90 divided by 60, which will be 3/2. Y is going to be equal to dy over d. That is going to be -150 divided by 60, and that will be equal to negative. They both have common factors of 30. That's going to be equal to -5/2. And then finally, z is going to be equal to dz divided by d. That is going to be 360 divided by 60, which of course is 6. So our solution is going to be 3/2, -5/2, and then 6. Our last example is to show that Cramer's rule does not apply for this particular system. And to do that, all we need to show is that this determinant is equal to 0. And there actually is a couple of ways to do that. The first thing that we can do is we can actually invoke Theorem 6. And how is Theorem 6 going to work for us? Well, first let's create our determinant. Let's create our determinant for d. So d is going to be equal to 1, -3, 2, 3, 1, -4, -9, -3, and then 12. Now using Theorem 6, I can actually revise row 3 by adding 3 times row 2 to it. We can actually do that, and that will not change the value of the determinant relative to Theorem 6. So I'm going to add 3 times row 2. And what is that going to do for me? Okay, well then for the first two rows are going to be the same. 1, -3, 2, 3, 1, -4. And then for this one, we're going to have 9 plus 3 times 3. Or I'm sorry, that'll be -9 plus 9. Then I'm going to have -3 plus 3 times 1. And then I'm going to have 12 plus 3 times -4, which will be -12. And actually, let me rewrite these so that they actually coincide with the other ones. So that will give me 3, 1, -4, 1, -3, 2. Okay, so there's our new determinant. Of course, I can simplify the third column, and that will give me 1, -3, 2, 3, 1, -4, 0, 0, 0. And what is does the first column tell us? If any row or any column is full of zeros, then this has to be equal to 0. If this determinant is equal to 0, Cramer's rule does not apply. You have to solve it. You have to solve it in another fashion if a solution exists. And if you wanted to compute this directly using any rule that you would like, you would come up with the exact same result. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.